Hi everyone, it's Coach Fred here, and today I'm going to be going over circles for the SAT or ACT. What do you need to know? So this is part one, because I think it could be a long video and I don't want it to be too long. But I was on a run just a few minutes ago and I came right in and I wanted to get this video done because I just was thinking there's so many little things about circles that you could forget from geometry. So, all right, so let's talk about circles. They are going to give you two formulas for circles on the test. They're going to give you the area formula, which is pi r squared. That's going to be on the SAT. They're going to give you the formula. And the circumference formula is 2 pi r. So on the ACT, they won't give it to you. On the SAT, they will. But I remember that, like, when you guys learn about circles when you're little, you tend to put a dot in the middle and draw the radius straight out like that. And I got to tell you, it's really not a good way to do it. Why? Well, because what you might not be thinking about is that circles have hidden triangles. They have hidden triangles in them. And if I draw a radius like that, I don't even get close to seeing a hidden triangle. All right, so my suggestion has always been when I teach this, when you're going to draw a radius like this. I know that's, I don't know why I can't draw a straight line today. Draw it like this. Let's try again. And like this, because then if you connect them, voila, the hidden triangle. All right, I'm going to actually do this with my measuring tool. So if you draw the radius like this, and then maybe like this, we know that radiuses of a circle are all equal, so they're congruent. And then do you see that if you connect the endpoints, you have a hidden triangle? In this case, a hidden isosceles triangle. So we know so much more now. We know that these base angles right here and here would be equal. We know the radiuses are equal, and you know what else? If I draw an altitude straight down off that circle, we know that it's bisecting this and this and the arcs as well, okay? So those are some really nice things to be able to see about a circle. Now, I also want to talk about the angles of a circle and the arc measure of a circle. So let me erase this and let's start over, okay? So this angle that is created right here with the two radiuses, that is called a central angle. And it is a rotational measurement. It is a degree measure. So we could say it's like 30 degrees. Now, the arc that it cuts off, so this guy, that's the arc it cuts off, also has a degree measure, which we would say is also 30 degrees, because the central angle of a circle is equal to the length of its arc. All right, there's another angle of a circle that's really helpful to know. It's called an inscribed angle. And this angle right here also has a relationship with the central angle. It's half the measure of the central angle. And its measure would be then, in this case, 15 degrees. Now, you might not remember that. The most important one to know is that central angle, okay? But you can also use hidden triangles to figure all of this out. So here's an SAT example. Point P is the center of the circle in the figure above. What is the value of x? So I'm trying to find this x right here, and I have 20 degrees here and here. So I'm actually going to look for hidden triangles, because remember, if I have hidden triangles, I have congruent sides. So if I connect that and that, I can see now I have a hidden triangle here and here. These are two isosceles triangles. Why? Well, because all the radius are equal. So if this is 20 degrees right here, then this is 20 degrees right here. And same thing over here. If this is 20 degrees, then this is 20 degrees. That makes sense? Okay, so I know that the inscribed angle then is 40 degrees, which makes the central angle 80 degrees. All right, let's pretend we forgot that. If we forgot that, and we were able to find the hidden triangles, and we had 20 and 20, Well, then we have the three angles of a triangle here, so this would have to be 180 minus 40, so that would have to be 140 degrees, this angle right here. And then this angle right here would also have to be 140 degrees. And then all the way around, all three of those would have to be 360 degrees. So 360 minus 280 would also give me 80 degrees. So again, I want you to absolutely think about the theorems with the central angle and the inscribed angle, but also remember that circles are a great way for you to look for hidden triangles, hidden isosceles triangles. Why? Because all the radius in that circle are equal. All right, let's move on. Another really important topic on the test that could be on the test relates to circles' arc length and the area of a sector. Those are just mathy words, right? Arc length. Arc length is a piece of the circumference of a circle. Piece of the circumference. And area of a sector is a piece of the area. They both have proportional relationships with the central angle. Proportional relationships. With the central angle. All right, so what do I mean by that? Well, let's pretend that I give you a little piece of a circle like that, and I want to find the arc length. So this is the arc length. I'm going to call the arc length S, okay? And I tell you that the radius of the circle is 4, and this degree here, the central angle, is 60 degrees. So I want you to think about that. That 60 degrees is of 360. So the proportional relationship has to do with that angle measure. And it's a part to whole relationship. I always like to think of it when I think of both area of a sector and arc length as part to whole must equal part to whole. The one part, the left part, think of it as the angle measures, okay? The angle measures. And the part to whole either as the circumference or the area, okay? All right, so what do I mean by that? Well, let's look at this one. We're trying to find the arc length, which we're going to call S. That's a part of the circumference. So the part of the angle measures would be 60. The whole angle measure of a circle, the whole rotation around a circle is 360 degrees. The part of the circumference is what I'm looking for, the arc length, and the whole circumference would be 2 pi r. Okay, so I'm actually looking for 1/6 of the radius is 4, so 8 pi. Okay, so I can cross multiply right here and get 6s equals 8 pi and then divide by 6. So s is equal to 4 pi over 3. Now, they could give you a free response with that, or and if they did, it would likely they'd say round, so you'd be able to put pi in your calculator, or this would be a multiple choice question. Okay. Now the same would hold true if this were I wanted the area of the sector. The area of the sector would be like if you think of this as a pizza, slice of pizza, it's like the cheese and everything and the crust all together, whereas arc length's like the crust. So the same relationship would hold. So we'll call the area of the sector, we'll use the variable k, okay? So that would be, again, 1/6 equals k over, now I gotta change to the area formula, pi r squared, so 16 pi. Again, we're gonna cross multiply, 16 pi equals 6k, and I'm gonna divide by 6. And so the area of the sector would be, what is that, 8 pi over 3? All right, let's look at some examples that you might see on the SAT. The circle above with center O has a circumference of 36. So we know the entire circumference is 36. What is the length of minor arc AC? Minor arc just means an arc less than 180 degrees, so don't worry about that word. But they want the length of this. Okay, so it's a proportional relationship with the central angle. I can clearly see that the proportional relationship angle is 90. The central angle is 90. So that would be 90 over 360, which would be 1/4. So I want 1/4 of the circumference. So 1/4 of 36, which would be 9. So that's like an easy level problem with arc length. All right, here's one with area. Point C is the center of the circle above. What fraction of the area of the circle is the area of the shaded region? So here it's just looking for the fractional area. Well, we know that we would take that central angle, we would put it over 360, and so that would be, let's see, 10 goes into them, right? 10 over 36. Oh, could have done more, right? I could have done 20. So 2 goes into 10 5 times, and 2 goes into 36 18 times. So the fractional relationship would be 5/18 of the entire area of the circle. Okay, does that make sense? Okay, the last thing I want to talk about in this video is the equation for the area of a circle in the coordinate plane. You might remember that you can draw circles in the coordinate plane. Here, let me just draw a quick coordinate plane for you, like that. I could draw a circle if I wanted in the coordinate plane, like this, okay? But I want to be able to find its area, right? And so there's a couple things. I might want its area, I might want its circumference, or I might just want to know its equation. Well, the equation of a circle is x minus h squared plus y minus k squared equals r squared. Now, I'm not going to go into where this comes from because you should have learned that in your Algebra 2 class, but I'm hoping that you notice that it looks similar to the Pythagorean theorem, a squared plus b squared equals c squared. It also resembles the distance formula, which is another way to look at the Pythagorean theorem. Okay, but h and k represent the center of the circle. The center of the circle, and r is the radius of the circle. So let's pretend for a second that this circle right here has a center of, how about -5, 4. And we're going to say that the radius, something like that, the radius is 10. So that would mean that my equation would be x plus 5 squared plus y minus 4 squared equals 100. And that gives me the equation of a circle. All right, we're going to talk more about this equation of a circle because on the SAT you have to be able to move from standard form and general form into this form for standard form of a circle. And we'll talk more about the types of questions that you could look at in my next video. Okay? All right, guys, hopefully that was helpful. Have a great day.